Right, so last week, VC from Socket shared this idea on Ethereum research coined filler vaults, which is a mechanism to deepen cross-chain liquidity via hyperliquid style vaults for intent markets. In this video, I want to make this a little bit more practical by taking you through an MVP that I have built in order to demonstrate how easily this could actually be built out. But before getting practical, let's actually look at a few problems the intent-based interop market currently faces and why these filler vaults could potentially alleviate some of these problems. The first problem here is liquidity. In this screenshot, you can see a user attempting to bridge 600,000 DAI from Arbitrum 1 to Optimism via the across bridge. Well, unfortunately, there's no filler available to serve this user. This obviously isn't great in terms of UX. And keep in mind, this is a blue chip asset being bridged between two of the major L2s. Now, you can imagine that the liquidity for the long tail market is 10x worse. Imagine someone attempting to bridge a niche token or bridging to a new chain. Well, you're lucky if there's any liquidity available at all. The second problem here is the heavy concentration of fillers within these markets. This is showing some statistics here from the across bridge. And here you can see that 63% of the total volume of that bridge is being cleared by a single solver. Now, I don't think anyone is preaching for endless competition because these fillers face high entry costs and also congestion costs and so on. But there's a healthy degree of competition needed in order to prevent monopolistic pricing dynamics. And no one wants these chain abstracted experiences across the Ethereum L2 landscape to end up being accompanied by some kind of heavy convenience tax burden. Right, so now that we better understand these problems, let's have a look at how these filler vaults attempt to improve the situation. So broadly speaking, these filler vaults are an attempt to open up the gates of capital to deepen the liquidity in these intent-based interop markets. This is very similar to what Hyperliquid did. Hyperliquid launched these HLP vaults that channeled liquidity to the perps exchange and thereby made it very competitive. Now, we have a couple of advantages that emerge from these filler vaults. One, of course, is the democratization of fee generation of these filling activities. But I think most importantly is that these filler vaults would provide this very effective mechanism for anyone to support a given route or a given token within the interop space. So for instance, imagine you're a new L2 or even an established L2 and you want to improve the onboarding experience or the general bridging experience towards your chain. Well, you could spin up a filler vault yourself that is connected to a strategy that fills specifically intents that are targeting your chain as the destination chain. And well, you could either fund it yourself or you could have your community rally behind it, for example. So to sum it up, these filler vaults really are an attempt to deepen the liquidity in the intent-based markets across the board. So how do they actually work? Let's have a look. Right, so the broad mental model here is that these on-chain vaults provide capital to off-chain filling strategies. And these off-chain filling strategies are essentially verifiable scripts that define everything from rebalancing, filling logic, and so on. And by verifiability here, I mean is that they can be verified in various forms. So for example, you could have a setup in which a vault requires a ZK proof to verify the correct execution of the filling strategy. It could also be set up to just get an attestation of a trusted authority to attest to the correct execution, or a bunch of trusted authorities and a quorum to be reached there, or you could have the whole filling strategy be run in a TE. It's really up to the market and capital allocators to decide what kind of guarantees they require. So let's have a look at how we are going to build this. Essentially, all we need is some kind of off-chain infrastructure that hosts these various strategies, and we need an on-chain verification mechanism to attest to the correct execution of these strategies. And after approval, the on-chain liquidity provided by the vault can then be used. So luckily, Socket provides the various Lego pieces that we need here. And it turns out that using Socket, all we have to do is write 2 smart contracts in order to deploy a vault with a given strategy. And these 2 contracts are the filler strategy itself, as well as the on-chain vault smart contract that provides the liquidity to it. So before we want to dive into the code itself, I think it's worth mentioning a few words about Socket. So Socket essentially is this EVM-powered server which abstracts away for you as a developer all the complexities that arise from building cross-chain. Meaning that you don't need to care about reliable RPC connections, you don't need to think about the complexities that arise from asynchronous flow across these chains and so on. So from a dev perspective, all you really have to think about is writing your smart contract as if all these various L2s lived in one single synchronous execution domain. So if you think about it, this comes in very handy when it comes to our filling strategies, because they need to do various reads from various chains in order to decide how to fill and when to fill. So on top of that, Socket provides these set of on-chain contracts referred to as switchboards that offer a very modular approach to security that these on-chain vaults can leverage in order to verify off-chain execution. I think you'll get a good understanding of what Socket provides now that we go into the implementation of the MVP that I've built. But if you want a deeper dive into Socket's architecture, I have done a video on that specifically a couple of weeks back, and I've added the link to it in the show notes. So pause this video here and check out the other video first, or let's dive into the code right away. Right, with that in mind, let's look into this MVP I have built in order to demonstrate how simple it is to build these filler vaults in practice and make this a real product potentially. So, of course, this MVP is far from being production ready, just as a disclaimer. And the goal of the MVP really is to demonstrate the end-to-end flow in its most simple form. And in that respect, I am just supporting an action to bridge ease from Arbitrum Sepolia to Optimism Sepolia. That means this MVP basically deploys a filler strategy that listens to intents that are configured to bridge ease from Arbitrum Sepolia to Optimism Sepolia. And that filler strategy taps into an on-chain connected vault, which provides the liquidity in order to fill it successfully on the destination chain. Also worth mentioning that in this MVP, I have opted to use a cross-protocol for intent settlement. So let's look at the various components that are needed to make this work. Actually, we'll only be looking at 2 of these components because the rest is implementation details and not really relevant. So the first relevant component is the filler vault, which is just an ERC 4.626 compliant vault into which anyone can deposit ease into to provide liquidity for intent filling. Now, worth mentioning is that in this tutorial, we only will need to deploy it on Optimism Sepolia because that is the destination chain. And since we are only supporting the one directional flow of bridging ease from Arbitrum Sepolia to Optimism Sepolia, we only need liquidity on that chain. And the second relevant component is this filler strategy. This is the filler strategy that defines the logic of filling intents and will be deployed on Socket's off-chain infrastructure. Right, so before we dive into the code, I think it's good to zoom out and get the bird's eye perspective on the setup if you want. So on the top here, above this line, you have the off-chain Socket world, so to say. And on the bottom left, we have Arbitrum, which is the source chain in our end-to-end flow. And on the right side, we have the Optimism Sepolia chain, which is the destination chain in our flow. Now, our filler strategy is deployed to Socket, which runs this EVM version with some superpowers to manage asynchronous flow and so on. In Socket, this is referred to as EVMX. Now, essentially, Socket allows us to listen to events emitted on the source chain. And specifically, our strategy listens to intents that are auctioned off by the across protocol. Now, it's a prerequisite here that you're familiar with the across protocol and specifically its hub and spoke spool model. So our Phyllis strategy is listening to events by the across spoke pool contract on the source chain, and then it processes it if it deems it an intent to be filled. In our case, that is if it's an intent configured to bridge ease from Arbitrum Sepolia to Optimism Sepolia, then it forwards it as a payload, and that payload is being picked up and relayed by so-called transmitters, which are off-chain actors that bring the payload to be executed on-chain. They bring it to a contract referred to as socket, and that contract is provided by socket, obviously, and makes sure that the security configured by this vault is being respected. The configured security required by the filler vault is essentially implemented in the already mentioned switchboard contract by socket. And in the case of our MVP, we have made use of socket's fast switchboard, which basically is a verification mechanism that just needs an attestation by a trusted authority that runs this off-chain socket infrastructure. But as already mentioned earlier, this switchboard could also be configured to verify a ZK proof, or could verify to have received an attestation by a TE that executed the strategy, and so on. Anyway, once the switchboard approves on the payload, the socket contract forwards the payload to the filler vault, and the filler vault then eventually fills the intent by making use of its liquidity by calling fill relay on the across spoke pool contract on the destination chain. So maybe I can make this even more obvious by showing this little flow diagram. So our flow basically looks like this. A user starts off with the intention to bridge ease from Arbitrum Sepolia, the source chain, to Optimism Sepolia. The user does so by depositing into the across spoke pool contract. Then via socket, our filler strategy is notified of that intent being auctioned off by a cross protocol and executes the given strategy. If our strategy then determines that it wants to fill the intent, it prepares a payload. That payload gets then verified on-chain through sockets on-chain contracts via the switchboard and so on that has been configured by the filler vault. If that verification is successful, the payload gets forwarded to the filler vault, and the filler vault then uses its liquidity to fill the intent on the across spoke pool contract on the destination chain, which is Optimism Sepolia in our case. Right, so I think we're ready to dive into the code, and I think the best way to get started is to look at the contracts in sequence of the flow. So let's start with our filler strategy. And our filler strategy contract, as you can see, inherits from the Up Gateway base contract, which is a contract provided by Socket Protocol. And relevant for us is that this Up Gateway base contract allows our contract on Socket to handle asynchronous flow. And it also helps us to virtualize various on-chain addresses as so-called forwarder addresses. It does much more than that, but the best way to learn about it is by going through Socket's documentation itself. So our filler strategy does two important things, which I'm going to cover. First, it allows us to deploy its on-chain connected filler vault. So all we're doing here is preparing the payload for the deployment, and then the deployment itself is provided by a method that we inherit from the Up Gateway base. So basically it's abstracted away from us. We don't really need to care about it. But you'll notice that there is this interesting async modifier here that we need to use for this method. And the reason for that is that the deployment of the vault on-chain is obviously an action that is asynchronous in nature. And behind the scenes, Socket basically creates a promise here and queues this payload to be executed. And once it has been executed on-chain, successfully or not, that promise gets resolved. And if we had registered some callback or something to be executed, that would execute. But in our case, we have not. What does happen, however, after this promise has been resolved, is that Socket creates a virtual representation of our on-chain deployed vault. And that is referred to as a forward address. And as you'll see later, is that we will actually make use of that forward address when we need to call our on-chain vault from our strategy. Anyway, that's the deployment. Next is the actual intent processing. That is where we define our strategy and how we want to fill intents. So as I have already mentioned, our strategy is the most simple you can think of. We basically make sure that we only fill intents that are configured to bridge ease from Arbitrum Sepolia to Optimism Sepolia. And all our strategy really does after that is that it prepares a payload that calls a given method on our vault contract and instructs it to fill a given intent using its liquidity. Additionally, we make use of this set timeout method. Again, this is something provided by the App Gateway base contract from which we inherit, which provides these precompiles. And the reason we use this set timeout is that we want to be able to configure this strategy's risk tolerance towards finality. So we have this fill delay in seconds parameter, which we set in the constructor method. And later on, we'll see that when we deploy all this, we'll actually deploy two strategies with their respective vaults on chain, because we want to see one which has an aggressive approach towards finality, whereas the other will be more conservative. Right, so I think this sums it up in terms of the filler strategy. Next, let's look at the filler vault, which is deployed on chain. So the filler vault contract really is a very simple implementation of the ERC 4626 standard. But importantly, it inherits from this plug-based contract. And this plug-based contract is provided by Socket Protocol. Now, plug-based, as the name already suggests, is a way to plug into Socket's infrastructure, so to say. For example, it would allow this contract to call a method of a contract that is deployed on Socket, for example. Also, it provides a modifier called only Socket, which we make use of here. And this modifier makes sure that only the Socket contract can call this method and has gone through the relevant verification through the configured switchboard. So that's what plug-based provides. Now, what about the implementation of this filler vault? I think all of this is basic ERC 4626 stuff, so we can ignore it. And the only relevant method here is this execute intent method, which is protected by this only Socket modifier. And this method essentially takes in some relay data that contains the information about the intent to be filled, and then calls the spoke pool contract of the across protocol to fill the intent. Now, there's some details worth mentioning here, because as you can see, we don't call the fill relay method on the across spoke pool contract directly. And the reason is that we have an in-between contract here called executor.sol. And the executor.sol contract is the contract address that is specified as the exclusive relayer of the intent that we initially sent to across on Arbitrum Sepolia. So what we do instead of calling fill relay directly is that we transfer the output amount of the output token specified in the intent to this executor contract. And then on this executor contract, which I will show to you now, we call this execute intent method. And this execute intent method basically does two things. First, it approves the output amount of the output token specified in this intent to the spoke pool contract, and then calls fill relay on the spoke pool contract with the given intent data specified within this relay data input argument. And this is pretty much all there is to these filler vaults. Importantly, of course, this only Socket modifier makes sure that the payload that has been prepared by our filler strategy goes through the Socket contract and through the configured verification set in the switchboard that has been configured by this filler vault. Hence, this modifier is very crucial here and is provided by Socket out of the box. Right, but I think this kind of sums it up in terms of what we need to know about the contracts. Let's now deploy everything and see what this end-to-end flow looks like. By the way, I have added the GitHub link to this code base in the show notes, so I highly recommend that you follow along if you really want to understand what's going on. I'm not going to go through all these prerequisites that are described here, but you'll need to follow the instructions in order to get your end-to-end flow working. So first thing we're going to do is to deploy the executor contract that I mentioned earlier, which acts as the exclusive relayer for the various strategies and vaults that we want to deploy. So once this is deployed, we're going to deploy this on the destination chain, obviously, where we're going to fill the intent, which is Optimism Sepolia. Next, we're going to deploy all contracts that reside on socket. That includes 2 filler strategies because we want to deploy one aggressive and one conservative strategy when it comes to finality, as we already mentioned earlier. So I'm going to show you the script quickly to show you the difference. And yeah, here we're deploying the 2 strategies, and you can see that one has configured a delay to executing a given intent of 2 seconds, whereas the other filler strategy has a configured delay of 30 seconds to execute a given strategy. So the latter here is what we refer to as a conservative filler because it's more conservative with regards to source chain finality, whereas the other one is aggressive because it only waits 2 seconds. Right, so our filler strategies have been deployed and we'll have to add them to our environment variables. Next, we'll have to deposit some fees in what Socket refers to as the fees plug. And these fees are needed in order to compensate these off-chain transmitters to relay payloads on-chain. Perfect, that looks good. Next, we're going to deploy the on-chain vaults, and we're going to deploy them, as we've seen earlier, through the filler strategies themselves. So first, we're going to deploy the conservative vault that is connected to the conservative filler strategy. Then we're going to deploy the aggressive vault that is linked to the aggressive filler strategy. And then we're also going to deploy a spoke pools wrapper, which I didn't mention until now because it's not really relevant. The reason we have this right now is that Socket doesn't support listening to events of any arbitrary contract, but can currently only listen to events emitted by socket plugs. So essentially, we are deploying a wrapper around the spoke pool contract of across on the source chain Arbitrum in order to inform our strategies about an intent being auctioned off. Cool. So now that we have deployed all on-chain contracts, that is the spoke pool wrapper on the source chain and the 2 filler vaults on the destination chain, I'm going to run a script real quick to get the addresses of the various on-chain contracts that we have deployed. We deployed them through contracts that are deployed on Socket, and hence we need to run a little script to get the on-chain addresses via Socket. Perfect, here they are. And then you just need to add them to the environment variables as well. Perfect, I think we're set. And all we need to do is fund those vaults with some ease. And then we can fire off an intent and see it being picked up by our strategies and filled by our on-chain vaults. But in order to make the whole thing a little bit more visual, I've built a front end to visualize these vaults and how they pick up intents and fill them accordingly. So what I am quickly going to do is adding these addresses to our front end so that it indexes everything correctly. Right, so this is done, and this is what our front end looks like. So basically we have the aggressive filler vault on the left and the conservative filler vault on the right. And now I'm going to run a little script that is going to deposit some ease into both of these vaults. Perfect. So the assumption here basically is that the aggressive filler is a little bit more risky and will attract less capital. Here we have deposit 0.04 ETH, and the conservative filler vault will attract more capital because it's less risky, and therefore it has a TVL of 0.08 ETH. Cool, so now we can test all of this by firing off an intent, and in the UI I have also added a little bridging interface that essentially allows us to bridge ETH from Arbitrum Sepolia to Optimism Sepolia via a cross protocol. So let's try this by bridging 0.02 ETH, and what we would expect is the aggressive filler to pick up this intent and fill it successfully because it is much faster as it waits only for 2 seconds to execute an intent. Perfect, that worked. And now let's try to bridge a larger amount, say 0.06 ETH. Well, what we should expect is that the aggressive filler will attempt to fill this strategy, but it does not have enough capital available, whereas the conservative filler will be successful in filling this intent because there's enough capital available in that vault. However, this should take a little longer because, as we've seen, we have configured the conservative filler strategy to wait for 30 seconds for the source chain to reach some kind of finality. Right, so I skipped the wait here and also resized the front end in order to properly show in this recording. But basically what happened after 30 seconds is that, as expected, the conservative filler strategy waited for 30 seconds of source chain finality and then relayed the intent to the conservative filler vault to be executed and filled. Now let's try to make a little sense of these numbers here. If you can recall, the aggressive filler vault was seeded with 0.04 ETH. And then, as a first bridging action, we bridged 0.02 ETH from Arbitrum to Optimism Sepolia. As a result, we saw this filler vault pick up the intent and fill it. However, the TVL dropped by 0.01 ETH and total fees earned shows an amount of 0.01 ETH. So essentially what happened is that the intent that was fired off here through the bridging action had the input amount configured as 0.02 ETH, what we inputted here, and the output amount was configured as 0.01 ETH. So essentially, the fee is the difference between the two, so 0.01 ETH. And the reason that the TVL dropped from 0.04 ETH to 0.03 ETH is that it had to provide this liquidity of 0.01 ETH, the output amount, in order to fill the intent and send it to the recipient of the bridging action. Now, after a cross settlement, this TVL will increase by the input amount that was specified, the 0.02 ETH, meaning that this TVL would increase to 0.05 ETH, which is the sum of the initial deposit, 0.04 ETH, and the fee earned by filling the intent of 0.01 ETH. And the numbers here can be interpreted exactly in the same way. Anyway, I hope this little demonstration made sense and gives an idea about how these filler vaults could be built. It would be awesome if anyone is attempting to build this in any form or shape for production purposes. I'm happy to help out in any way. Also, if you have any questions about integrating Socket in some form, let me know. And yeah, I have shared the GitHub link to this code base, so you can go through it in more detail on your own and at your own pace.